Developed at the Mayo Clinic, Semantic Answers in Medicine resides at the intersection of data science and cognitive science, combining technology and human learning models, and can resolve the medical industry problems that we've highlighted. SAM establishes data patterns from reading information in the clinical information systems, such as the electronic health record legacy systems, patient documentation, referral documentation, physician SOAP notes, test results, reports, and even wearable patient data. All data is read and normalized within SAM's knowledge graphing engine. Knowledge graphs are automatically created within SAM to establish a patient context, a continuously evolving understanding of the patient's situation. As new information arrives, SAM appropriately updates its understanding, helping the clinician eliminate diagnostic potentials while adding new emphasis to the remaining potential diagnoses. Each data point within the care of a patient is available for evaluation, predictive analytics, and pattern recognition in near real time. In SAM, all knowledge graphs are domain-specific and have an underlying ontology, because there's no one-size-fits-all schema or ontology that is well suited for solving all problems or answering all queries. Deciding what makes for a good ontology is a challenge. Here in this presentation, we focus only on the patient perspective, but SAM's powerful intelligence could be rearranged into any of the following relative ontologies. To demonstrate how knowledge graphs are created, we'll begin with the patient entity. The patient entity starts with the most basic of information, such as the patient's name, gender, and date of birth. The data within a patient entity is grouped according to patient history, patient administrative and demographic information, clinical information for each episode of care, observed clinical information for each encounter with a clinician. The data is actually collected in the background without any required action on the part of the clinician. Here, we'll take a walk through an electronic health record for a patient named Sherry Wright and illustrate where information is found and how it is placed into a knowledge graph. Administrative and demographic information is collected and stored in the general and vocational fields of the graph, along with information about responsible parent or guardian for pediatric patients. Clinical history is collected including risk factors, family history, well-being, nutrition, medical history, exercise, and substance abuse information. Most episodes of care begin in a primary complaint, at which time the complaint is recorded. Vitals are taken, and next steps are identified. Each data point is added to the patient context under the episode of care. Because an understanding of a patient's situation develops over time, we record the evolving patient situation in individual patient encounters with the clinician. A review of physical systems and the reason for the patient visit often leads to a working diagnosis, which requires ordering of tests to perform a differential diagnosis. Each order in the computerized physician order entry system includes the working diagnosis or problem, along with the name of a procedure, test, or evaluation. This information is collected and sent to the patient context knowledge graph. Test results are reviewed to confirm or disprove a working diagnosis. For example, let's review a radiology report for a patient with suspected pulmonary embolism. Each report describes the finding of the imaging procedure. The finding is extracted from the report using SAM's natural language processing capability and then analyzed for its conclusion and placed in the imaging field studies of the knowledge graph along with other test results. Medication and dosing information is collected and placed in the medications field of the knowledge graph. Unstructured free text notes present the biggest challenge for information extraction systems. SAM addresses this problem by reading summary, SOAP, progressive, discharge, and operative notes and breaking down each into meaningful words and phrases. Each word or phrase is analyzed for its type and semantic meaning, resolution of pronouns and co-references, and its context to the caregiver. Words and phrases are stored in the notes field of the knowledge graph in a format called triplets. The triplet contains a category name, the word or phrase, and the relationship to that category. Each triplet is then processed by a machine learning algorithm to recognize patterns and relationships. Missing or incomplete fields are easily identified, allowing SAM to inform a clinician of information gaps. In addition to providing a framework for the storage of knowledge, the knowledge graphs are also available for iteration with clinicians, caregivers, and researchers. Clicking on an individual node of the graph results in a dialog displaying the contents of the node. In this example, we can see the medications a patient was taking at the time of the patient encounter and the family history for the patient, such as early death of both parents because of coronary artery disease. Critical to patient care and medical research is the ability to contextualize data in multiple dimensions. Within SAM's knowledge graphs, every data node variable can be evaluated longitudinally. Importantly, SAM can also evaluate each node or grouping of nodes in among a large data patient dataset for research or drug trial. We have barely scratched the surface on describing the implications of SAM's capability. SAM, for example, compares a patient's data pattern to the known data pattern within SAM's content corpus and suggests evidence-based practices for the patient's situation in any field of practice, whether cardiology, oncology, or pulmonology. SAM can compare a patient's data pattern to previous patients or even another current patient's data pattern and make an introduction to other physicians for consultation in near real time. The implications are immense. SAM extracts frozen data within various sources and builds a contextual understanding, thereby retaining its deep meaning and thus transforming information into actionable knowledge where the medical industry stakeholders can fully leverage technology to the benefit of mankind.